Hello and welcome all of you to this session of heat transfer. Today is the fourth lecture and today we'll be taking some numerical problems regarding the fundamentals which we had discussed in the previous lecture. So I would like to recapitulate what I have said in the previous lecture in a nutshell so that I can help you for this session. Now, we had basically applied the 3D time-dependent heat conduction equation for the case of plane walls. Now, in case of plane walls, we have assumed that it is a steady-state heat conduction problem. It is a one-dimensional heat conduction problem, as well as there is no case of thermal energy generation. So we have seen that the equation uh, of general heat conduction was reduced to a very minor one, and by the help of that equation we had derived the temperature distribution so that we can calculate the temperature at any instant or at any space within the plane walls. Okay, so and regarding this temperature distribution will help us to find the heat transfer rate within the plane walls. And we have seen this how this heat transfer rate can be seen in the from the perspective of, yeah, electricity transfer. That means we have seen that there is a uh, there is a similarity between the heat transfer process and the electricity transfer process. So from that similarities, we have defined the concept of thermal resistance. This thermal resistance concept have helped us to define the heat transfer characteristics for the composite plane walls, and for those cases where conjugate convection and conduction takes place. That means whenever you will see that convection and conduction are taking place simultaneously, the electrical analogy concept or the thermal resistance concept of conduction becomes very much important. And with this approach, we can solve numerical problems. So, these were the discussions which we had in the previous lecture. So regarding this analysis part, today we'll take some numerical problems and we'll find that what we have understood in the previous lecture. Okay, so let us start with the first problem. As you can see, uh, a certain configuration has been provided here. There are specifically four walls. This wall, uh, this is the first wall, this is the second one, this is the third one, and this is the fourth one. Now it is quite evident that the second and the third wall, they are uh, remaining in a parallel arrangement. Okay, so this is something interesting for you for this problem. So let us just read out this problem. For the configuration shown in the figure below and conditions specified, so this is the condition which is specified here. Determine the temperatures T2 and T3. The thermal conductivities are maintaining the relation K1 equal to K4 equal to K2 by 2 equal to K3 by 3 equal to K. So K is the general number here. Okay, so let us start the problem. So this wall and these two walls and this one, so there are four walls. These ones along with these two walls combinedly, these two walls combinedly and this one, they are arranged in a series circuit. Okay, but within this combined wall you can see that there are two different walls which are arranged in a parallel format. So what we have to do, we need to create a electrical circuit to define the heat transfer going on here. So just give me some time and I will draw the electrical circuit for you, and then we'll go on for the explanation part. Okay, So I have drawn the circuit here. Now you can see that Q is the rate of heat transfer which is taking place within these walls. The temperature at the leftmost surface of this wall is maintained at 1000 degrees Celsius, and for the heat transfer through this wall, the thermal resistance encountered by the heat Q is RTH1. Okay, and now for this wall, since this wall is in a parallel arrangement, we have to take two separate resistances for the heat transfer. Okay, so now you have to understand that this resistance, these two resistance, they are in a parallel arrangement, and if we find the equivalent resistance of these two, then we can say this one, this resistance, and the equivalent resistance for these two walls are in a circuit. Then we can find the total resistance which is encountered by the heat through its journey from this surface, from this point to this point. Then it would be the summation of RTH1. Okay, so it will be RTH1 plus R equivalent. Equivalent is because these two, RTH2 and RTH3, they are in a parallel arrangement. So we have to find an equivalent value for these resistances, and then we can plant it in a series mode. Okay, plus RTH4. Okay, now I would like to find the individual thermal resistances. Like, what will be the value of this RTH1? If you know, can you say? So it is very simple. It is T1 minus T2. You know, this T1 is the temperature of this end. So you can see it from the electrical circuit here. So this is for T1, this is T2, and you need to find the thermal resistance, right? So here, this is the thickness of this wall, so we don't need to take this value delta. We will give a x here, so x divided by k1 into a. Now here you can see that k1 is equal to k, so we will leave with k here, so k into a. So this is the thermal resistance for the plane wall which has a thickness of x and the area of a and a thermal conductivity of k1, and one side of this wall is maintained at 1000 degrees Celsius. Okay, now what would be the thermal resistance of the second case? That means for this case, so when heat is transferring or flowing through this wall, then it would be T2, right? It would be T2 minus T3, because this T2 and T3, they are the boundary temperatures, divided by, for this case you need to consider this K2, this is the thermal conductivity. So let us first deal with the thickness. So the thickness is 2x divided by the thermal conductivity, which is K2. Now here you can see K2 by 2 is equal to K. That means K2 is equal to 2K. So we will write 2K here. And what is the area here? The area is A by 4. So after simplifying, we will see we can write this as oh, I am very sorry. I'm very sorry. I have written this in the resistance format, but it will be actually in uh, it will be actually in heat format. Okay, so it will be actually in heat format. I am very sorry that I have confused you. So it will be in heat format. But if we need to find these resistances, then what will be the formula here? RTH1 will be equal to 2x by Ka, right? I hope you are understanding it now. So RTH1 is x by Ka. Now what will the value of this RTH2? So you can see this these two terms are alike. So it will be 4x by Ka. Okay, so it will be 4x by Ka. Okay, now let us find the thermal resistance for this case. So it will be RTH3. That means, first of all, just write down the thickness. It is 2x. And what is the thermal conductivity here? K3. Now see the relationship between K3 and K. K3 by 3 is equal to K. That means K will be simply 3K. And what is the area here? It is A by 4. So we can write 4 into 2 here. That means it will be 8. So ultimately we find that the thermal resistance for this wall would be 8x by 3Ka. Now see, this wall for which the thermal resistance is RTH2 and this one for which the thermal resistance is RTH3. They are arranged in a parallel way. Now we are interested to find the equivalent resistance. As I have mentioned that if we replace this by equivalent circuit, then we can say that this wall, and so you have to mind that we are talking about an equivalent wall here. Okay, so this equivalent one, and this one, they are now arranged in a series format, and then only we can add them up so that we can find the sum of thermal resistances. Okay, so we are interested to find the sum of thermal resistances. Only there is a parallel arrangement here. We need to find an equivalent circuit, equivalent resistance here. Then we need to just add it up. Okay, so RTH2 and RTH3, they are in parallel arrangement. Now we need to find this equivalent one. So what will be the formula? RTH2 into RTH. So this is simple physics. You know these things from class from the understanding of class 11 and or class 12. So it will be RTH3. Ultimately you will get a value of you need to calculate it by yourself, and ultimately you will get a value of 8x divided by 5Ka. Okay, so I'm not getting into the calculations. So now you have found out the equivalent value. So R equivalent is equal to 8x by 5Ka. Okay, now we don't need this. We don't need these things also, because we have already written the data here. So now let us find the thermal resistance for this wall. So it will be, so first you have to write down the thickness, which is 3x here, and then you have to write down the thermal conductivity here, which is K4, and K4 is equal to K. So it will be simply K, and then you need to find the area here. The area is 2A. So it will be 3x by 2Ka. Okay, so it will be 3x by 2Ka. So you have now uh, found out all the three required thermal resistances. That means now you can remove this circuit. Okay, you can remove this one, and you can place another one here, Okay, so now you have to mind that this has a temperature T3, but this resistance will be a equivalent one. So this equivalent resistance is created by the parallel arrangement of these two walls. Okay, so now you can see that these three resistances, they are in a arrangement, they are in a series arrangement. So we just need to sum it up so we can find the total thermal resistance. So if we sum it up, that means if we add these three separate values, which is RTH1 x by Ka, R equivalent, which is 8x by 5 Ka, and RTH4, which has found out to be 3x by 2 Ka, we will get a value of 41x. This becomes 41x divided by 10 Ka. So this is your sum of thermal resistances. Okay, so now I hope that this circuit will not be required most probably. Okay, just I think I would like to. So this RT refers to the total resistance, okay, which is 41x by 10 Ka. I hope you have understood how we are finding this RT. This is the summation of all these three. Okay, this is very simple. And this RTH4 becomes 3x by 2Ka. So this is only because we will require these values afterwards, because the problem is not completely solved. Okay, so we have found these values here. Okay, let us remove this circuit. Now you know that this Q is equal to T1 by T2 by RTH1, because the same heat is flowing through the different walls. So this is your T1, this was your T2. So T1 minus T2 by the thermal resistance RTH1, which is equal to T1 minus T4. This is your T4. Okay, and this is your T1 by the sum of thermal resistances. So now you can write that T1 minus T2 by RTH1 is equal to T1 minus T4 by RT. Now you know that this T1 is 1000. Okay, you know that this T1 is 1000. This is your T2. This RTH1 you have found as x divided by Ka. You know that T1 is 1000 degrees Celsius. This T4 is 400 degrees Celsius. Then T1 minus T4 would be 600. Very easy to understand. And we have found out this RT as 41x divided by 10 Ka. So you can understand that uh, this x by Ka terms would be they are alike terms, so they can be moved away from this equation, and simply after the basic solution we will get that T2 will get T2 after simple addition and multiplication. We will get T2 as 853.65 degrees Celsius. Okay, this is very simple to understand. I think you must have got it. Okay, so this is simple algebra here. This these terms will get removed from the equation. Um, this will be here, placed here. You need to multiply this 41 here, and then you can find out the calculations. Okay, So we have found out the value of T2. Now we'll be looking to find out the value of T3. So I am keeping it same as it is. Okay, don't okay, just let me rewrite this. So it will be 41x divided by Ka. Okay, now what we will be doing is that we will be equating these two equations. So from this understanding, you know the same heat is flowing through the different walls. So from this understanding, we can write that T3 minus T4 divided by the thermal resistance RTH4 would be equal to T1 minus T4 divided by sum of thermal resistances. So just give me some time. I'm just writing it here. T3 minus T4, and it will be RTH4. Okay, I think you have got it why I'm writing this. So it will be it will be RTH4. Okay, so T3, you don't know what is the value of T3 because this is your objective here, and this T4 you know, and this T4 is nothing but 400 degrees Celsius. And what is the value of this RTH4? It is 3 by 2 x by Ka. So after performing the simple multiplication and addition, so just simplifying the equation which you have got here, you will find that T3 will give you a value of 619.51 degrees Celsius. Okay, so the basic concept to solve this problem lies here. You need to understand that same heat is flowing through the different walls, and this can be represented via the temperature changes. And you need to understand that uh, this was arranged in a parallel way, so you need to convert it in the series format, and after that only you can calculate the resistances which are in a series format, and you can just add it up. Okay, so I hope you have understood this problem now, and let us move on to a different problem now, where we'll be encountering the case of combined conduction and convection problem. So let us move on to this problem. So this is your problem, the problem number 2. So here it is. The temperature at the inside and outside surfaces of brickwork of a furnace are maintained at 650 degrees Celsius and 250 degrees Celsius. Make calculations for percentage decrease in heat loss if thickness of the brickwork is increased by 100 degrees Celsius. That means the bricks had an initial thickness, and in this final case its thickness is getting doubled. Okay, the ambient temperature is 30 degrees Celsius, and assume that thermal conductivity of brickwork and convective heat transfer coefficient is unchanged after and before the increase in thickness. So just give me some time, I will draw it for you, which will surely help you to understand the problem in a much better way. So just give me some time and I will draw it. So here is the problem for you. Now you can see this green line indicates the initial condition of the brickwork. So it represents the initial thickness, which is taken as delta here. And the walls of this brick, they are maintained at temperatures T1 equal to 650 degrees Celsius and T2 equal to 250 degrees Celsius. So this side is the interface which starts to interact with the ambient uh, through convection. The ambient is kept at temperature 30 degrees Celsius. So it is quite obvious that you can equate the conduction process and the convection process, and you can also find out the relationship between this conduction and convection heat transfer processes at the steady state by using the formula. So we have already discussed this specific case previously. We have taken a specific case just a few minutes ago. So now I hope that you will understand this problem in a much better way and in a much faster way. So I'll be just writing the formulas and I'll revert back now. Okay, so this is the heat transferred via the convection mode. This is the heat transfer via the conduction mode through the plane wall. This is the heat transfer between this side of this plane wall with the ambient. So you know there is air present here. So heat transfer is going on by the mode of convection here. So this is convection, this is conduction, and this is the combined conduction and convection effect. Okay, now we have assumed that this plane wall has an unit area. Since they have an unit area, so you might get puzzled why I have taken this assumption of plane unit area, because at the end of the day you will see that there will be a term a. So to remove the complications, we have assumed that this area has the value of 1. So since this has a value of 1, we can simply remove these terms, and we will see that this thermal resistance, because of this combined conduction and convection effect, it also reduces to this. Okay, now you know the values of T1 and T2. You know the values of uh, T1 and T2 only. So if you try to relate these two equations, you will get T1 minus T0 by 1 by H plus delta by K is equal to T1 minus T2 divided by delta by K. Okay, so let us take this delta by K. Let delta by K is an arbitrary value C or something else. You can take whatsoever. So we can replace this one by C. Okay, so it will be C divided by C. Now you know the value of T1, it is 650, and you know the value of T2, it is 250. So here you can write 650, and here it would be 650 minus 250, so it will be 400. And after this, oh sorry, you also know the ambient temperature, it is 30 degrees Celsius. So ultimately you will get the value of 620. I'm sorry, I just missed the ambient temperature here. So now you can, after simplifying this equation, you can relate this C and this factor 1 by H. So it is after the calculation you will see that this is the relation. Okay, so I am not doing the calculation, obviously you will do it by yourself. So 0.458 C is equal to 1 by H. So this is the finding of this equation. Okay, so let us keep this relation because it will help us afterwards. Now if we move on to the second case, when the insulation is now twice, that means the thickness of the brickwork is increased by 100%. So this thickness is added up with this, that means the final thickness becomes 2 delta, right? And the final temperatures would be, that means this will be the T1, the leftmost side of the surface of this plane wall would be maintained at T1, and it would be interacting with this ambient which is kept at TA, and it is 300 degree Celsius. So these values would not change. So regarding that case, in that case, we can write that. So just let me clear these things. So we can write this Q2 will be equal to T1 minus T0 divided by the resistance, the thermal resistance because of conduction. Now it is quite obvious that since the thickness is doubled, it will be 2 delta by K plus 1 by H. Now you must remember that we have taken this factor delta by K as C, so we will write to C here. Okay, so thickness is doubled. Now the conduction is taking place, I'm sorry, through this mode, and the temperature is T2 here, or something else, T3. Okay, it will be like this: T1 minus T3 K into T1 minus T3 divided by 2 delta into A. So if you try to find out the thermal resistance, then it would be like in this format. Okay, so it is quite obvious that we have now found out that this Q2 can be related by this formula 2C plus 1 by H. Now the question is that we have already found a relation between the C and H, which can be provided here, and after providing that, we can we also know the value of this 650 minus 30 divided by 2C. uh, so just so it will be 2C plus 0.458C. So ultimately it would be 2.458C, right? And in the previous case I have missed to do the calculation. It would be like this: T1 minus T0 divided by C plus 1 by H. It was like this, if you remember. So in that case, okay, I'm very sorry here. You can take, in the previous case, the formula can be written in this format also. So this is the heat transfer rate when the insulation was not twice. Okay, it was simply uh, the thickness of the brick wall was K lambda. The thickness, I'm very sorry, the thickness of this brickwork was delta, and you know that we have taken this delta by K as C. Okay, so we know that T1 is 650, we know T2 is 250 degrees Celsius, and if we relate these two, then we will get 400 by C. Okay, we will get this 400. Okay, so this Q1 can be calculated as 400 by C, and we are doing this calculation since I remember that I also need to do this calculation, and this result will be found as 252.2 divided by C. Okay, so please recheck it once, because there may be some problems regarding the calculation part, but the concept is absolutely okay. So please recheck it once. Now we need to calculate the decrease in heat transfer. So if we are worried about the decrease, then uh, how we can calculate it? So initially it was Q1 and finally it became Q2. So we can decrease or the change, we will write this Q1 minus Q2 divided by Q1. Ultimately you will get a result of 40.66%. That means you need to put this value 400 by C divided by minus 252.2 divided by C, which would be divided by 400 by C. So and you will get this final result. Okay, so this was a combined conduction and convection problem where uh, initially the thickness was given to you and you need to find you have related the um, lambda by k factor. That means the thermal resistance because of the conduction. You know that the thermal resistance because of conduction is generally in this format. Since we have assumed the area of this wall is unity, so we have taken this A as 1 and the thermal uh, resistance factor for the conduction became delta by K, and 1 by H was your thermal resistance because of the convection going on with this surface, with the rightmost surface, and the ambient. Okay, and and then we found that these two can be related. Since we took this delta by k as c, we mentioned that this delta by c can be provided by a different factor as c, and then we related the c and 1 by h, and afterwards when the insulation was twice, we did the same thing, but in that case the thickness was doubled, so the conduction resistance also changed, and thereafter we found the heat transfer Q2 in terms of C. Same as Q2, we also found out Q1 in terms of C. Then we found the change, that was Q1 minus Q2 by Q1. Okay, so this was a combined conduction and convection problem. So I think you have understood the concepts of one-dimensional conduction equation and its application for the plane wall. We have solved two different problems. I hope that these two problems will give you an proper understanding of these concepts. So with this, I would like to end my lecture here, and I hope that if you face any kind of trouble, you can always mail me. You know my mail ID, and so let us see forward to the next lecture, which will be a discussion on the uh, one-dimensional steady-state heat conduction, but for the cylindrical surfaces. Today we have seen this equation for the plane walls, and in the next day we'll see the same equation, how it is applied for the cylindrical surfaces. So thank you and goodbye. So looking forward to the next lecture. Goodbye.